Hello, my name is Brian Crafton, and I will be presenting our work titled Automatic Generation of Translators for Packet-Based and Emerging Protocols. My co-authors are Arijit Raychowdhury and Sung-Kyu, and we are from the School of Electrical and Computer Engineering at Georgia Institute of Technology. First, I will go through the motivation and background, which are essential to understanding our research contribution. Then I will discuss the various parts of our tool flow, and lastly, I will present our results. A new trend in the production of SoCs is rapid and low-cost development using platforms such as FPGAs and System in Package using 2.5D silicon interposer technology. System in Package allows us to achieve higher yield with close to system-on-chip performance and enable design reuse of optimized components in the form of chiplets. FPGA tools and performance have been steadily maturing, enabling close to ASIC performance with dedicated on-chip DSPs and ARM CPUs. They're readily available in the cloud or as low-cost dev board solutions for prototyping. At the same time, an open source hardware movement has started with RISC-V, the Open Compute project, and an abundance of hardware projects open source on GitHub or various online platforms. So with frameworks like Silicon Interposer and FPGA in place, we can envision new design frameworks, IP catalogs of hundreds of vendor IP and chiplets for designers to choose from based on power, performance, and cost. The figure on the right illustrates this idea where we have three options to choose from, namely custom IP, open source IP, and commercial IP. After choosing IP, we might export the designs to our favorite tool and produce a Silicon Interposer-based microcontroller using an open source CPU and custom XPU, shown in the bottom left, or perhaps a FPGA-based DNA accelerator with commercial components from various vendors, shown in the bottom right. This new framework promises high-quality design, maximizing reuse, and expediting chip development. However, this idealized design framework faces one key issue: communication. IPs typically use different protocols, whether custom or standardized, and thus bridging or redesigning existing IP is prohibitive to mass integration. So for example, in the bottom figure, how can we make an open source CPU communicate with a brand new DNN accelerator if they use different protocols? Of course, we can create a bridge or redesign the IP, but doing so for all IP is counterproductive to our idealized framework. Furthermore, protocol standardization has been attempted many times in the past, but has yet to stick and limits design creativity. And so our objective is to automatically generate these translators using a tool flow and enable communication between any pair of IPs. So for instance, if we take the open source CPU and commercial NPU from before, we want to automatically generate a translator or bridge that can be used to enable communication. This is a relatively old research idea which dates back to the 1990s. So building off these ideas, we propose a new flow capable of handling most protocols used today. A high-level view of this tool flow is shown in the bottom right that we will detail over the course of this presentation. First, we create a language for modeling protocols called Protocol Description Language. Next, we describe protocols in this language and create data structures in the form of finite state machines modeling their behavior. Then, we create a unified FSM which models the integration of the two protocols. And finally, we generate RTL that serves as the translator. As an example, we can look at the commonly used AXI protocol. On the left side, we are showing an example waveform of a 4-read burst. On the right side, we show the corresponding finite state machine that models this protocol. The grayed out paths in the finite state machine represent other burst lengths that may be used, in this case single read and 2-burst read. We only show these 3 paths for simplicity. In our state machine, the states simply keep track of what part of the protocol we are in. The edges contain conditions for state transitions as well as the data transactions that occur. So to transition from state 1 to state 2, we need valid and ready to be high and ARLen to be 4. If ARLen had been 1 or 2, we could have transitioned to one of the grayed out states. Next, we will continue making state transitions as long as valid and ready remain high. And we also note that we will receive data on these transactions in the form of our data. As a second example, we look at a standard custom packet-based protocol. Again, we look at only a subset of this protocol for simplicity, but it's clear how it generalizes. On the left, we show a read request packet and a read response packet. The read request packet consists of 2 flits. The first is the header, and the second is a 1-flit body. Our read request packet specifies the length of the read request, and the body contains a 32-bit address for the data. The read response packet consists of 5 flits, containing the same exact header as the read request, and 4 flits containing 32 bits each of read response data. On the right-hand side, we show the FSM corresponding to the protocol. The left side path models the read request, and the right side path models the read response. Both packets diverge from the common flit header, which is true for all packets in this protocol. Simple protocols such as I2C or SPI, or the subsets of protocols we've observed so far, can be modeled with a single finite state machine. However, more complex protocols used today have different interfaces that operate independent of one another. An example of this is the read and write interfaces in AXI. These interfaces are completely independent of each other. This means that we can be in any read state or any write state at the same exact time. To illustrate this idea, we show a read transaction and a write transaction occurring under AXI. The choice of burst length and actual timing of the read and write transactions is completely arbitrary. This means that the read could have happened one cycle earlier and the write could have happened one cycle later. If we wanted to model this with a single FSM, we would have to enable all these combinations, and this would cause a state space explosion. The solution to this problem is modeling AXI as a set of independent state machines. So now we understand some of the basic modeling principles. How can we generate finite state machines? Rather than defining a finite state machine as a set of states and edges, we can define a protocol description language, or PDL, to simplify the problem. The code can be written in text file and then parsed using standard Lex and Bison tools, just like C or Verilog code. After parsing the code, an abstract trajectory is generated, which can then be transformed into the underlying finite state machine expressed in the PDL code. In the PDL code, we define several necessary semantics to expressing protocols discussed so far. First, we require information about the signals or ports that make up the protocol. Like Verilog, the direction, input, or output must be defined. Furthermore, the signal should be tagged as either control or data. Control means it is used as a condition for state transition. So for example, valid and ready are common control signals. Data implies the signal is the actual read, write, or address data that is being sent or received. The importance of defining control and data is the tool knows whether the signal should be sent to the other protocol or if it is just a means of controlling the state machine. The second part of the definition is called the behavior. So a behavior statement is equivalent to a finite state machine, and thus many behavior statements corresponding to many finite state machines can be used. We show a simple behavior statement which contains read bursts of size 1 and 2. We model the conditions using the ampersand symbol and a list of arguments, and following the conditions we specify the transaction that follows. In this case, we are receiving our data. In the example, we show simple syntax for a subset of the protocol, but for the actual protocol, we support generate loops and parameterization that make the code more concise and human readable. So what about packet-based protocols? Well, it's the same idea, however, some new syntax is required. Packets are simple in structure and can be viewed as a list of flits. In this example, we are showing part of our packet-based protocol for the read response packet discussed earlier. The main idea used to specify packet-based protocols is to specify flits or subpackets, and then concatenate them together to form the full packet that occurs over several cycles. For example, we specify the packet header and a read response flit with these two packet definitions. Then we string them together to form the single or two burst read response packet shown here. Since all packets contain the same packet header, we branch after this header and specify the condition based on the command code for each packet to be sent. In this case, a command code value of 32 in the packet header specifies a single read response will occur, and a command code of 33 specifies a two burst read response. We should note that while syntax for these protocols does have some major differences, all the primitives like control, data, in, out, and the ports remain the same. Furthermore, both packet-based and bus protocols are compiled to the same finite state machine structure, and thus the tool sees no difference between a packet-based or bus protocol. This difference occurs just at the syntax level. So this brings us to the finite state machine integration part of the flow. Now that we have a method to generate models of our protocols, we can develop algorithms to take these data structures and synthesize a translator. So how can we integrate two finite state machines and then create a final finite state machine which will serve as a translator for the two protocols? Or first, what is even meant by integrating two finite state machines? Well, first we can define a goal. Our goal is to enable protocol 1 to send signals tagged with data in the PDL code to protocol 2. The reason we are concerned with sending only data is because control signals are not transferred, but rather just translated. So for example, let's look at the AXI example from before and attempt to send data to a simplified AHB protocol. In this example, our goal is to send 4 read transactions between the two protocols. Looking at the highlighted paths, the solution is clear. our data from AXI should be transferred as HR data for AHB. The naming convention is just different. However, the control signal ARLN is not important to transfer to AHB. It just indicates AXI is sending 4 transactions, unless the translator's job is to tell the AHB IP that 4 transactions are coming. Thus, the translator will see ARLN equals 4 and should set hburst to 1 for AHB. That covers how to translate one sequence, but how can we define success for finite state machine integration? Well, for all sequences in protocol 1, we should be able to translate the control signals and successfully deliver the data to protocol 2. We solve this problem by traversing both protocols and building a table of all valid sequences which look like this. For AXI, we can identify 3 paths, and in AHB, we can identify 2 paths. We keep track of the number of cycles for each path, as well as the transactions sent or received along each one. Then we loop through all the paths in the master protocol and identify the ones that send data. For each of these paths, we perform a lookup operation in the slave protocol table to identify paths we can use to satisfy the master path. Looking at our example, we can match path 1 in AXI to path 1 in AHB, since they both contain 1 transaction. For path 2 in AXI, it is a bit trickier, since there is no 2 transaction path in AHB. So we must break it up into 2 single transactions for AHB. Lastly, looking at path 3, we have a decision to make. We can either break the 4 transaction burst into 4 single transactions, or we can send it as the 4 transaction burst to AHB. Naturally, we will pick the 4 transaction burst to AHB, and this is why we track the number of cycles for each path, because we can break ties by choosing the option with the lowest latency. After picking paths that match and also minimize latency between the 2 protocols, we have to merge each pair of paths. We call this process scheduling, where the goal is to take 2 matching paths and generate 1 merged path. Expanding off of our previous example, we can attempt to merge 2 matched paths. Paths 1 and 3 were easy, since they were the same burst length and had the same timing. But what do we do when the signal timing doesn't match, as in the case of example 2, where a 2-burst read from AXI was matched to 2 single reads in AHB? Looking at this figure, we can either buffer transactions from AXI to AHB and allow AXI to send freely, or we can stall transactions such that the timing lines up between the 2 protocols. Although this is a small example, buffering large bursts can be expensive, and sometimes it is preferable to stall to minimize area. But how can we stall? Consider what condition allows AXI to send the second transaction, the ready signal. So to stall, the translator should deassert the ready signal until the timing matches. We show this in the new timing diagram on the right, where 2 bubbles are inserted since the translator deasserts ready. Now this works fine assuming there is a condition to stall. But what if there is no condition to stall, meaning the burst cannot be stopped once started? Well, in this case, we're out of luck, and we must buffer all the transactions. Now that we can create a merged finite state machine that translates between 2 protocols, we need to generate RTL so that we can actually use this in a design. So this brings us to the final part of our flow, where we will export the finite state machine data structure into synthesizable Verilog code. We choose to export our design to Verilog code, but why Verilog code? Well, first of all, it's definitely easier than making a netlist. And second, commercial synthesis tools are really good, and we want to take advantage of years of research and optimization. To generate Verilog, we realize that all translators are comprised of the same basic components. And so we generate Verilog by instantiating these components one by one. First, we instantiate FIFOs at all data transaction ports to buffer data. Second, we need multiplexers to handle a couple of scenarios. The first scenario is for protocols with width mismatch. For example, if we were translating between a bus and serial protocol. The second scenario is for packet-based protocols, where data could come from a different section of the physical wires. The third building block is an address calculator to handle address offset between protocols. So if one protocol sends one address for 16 transactions, but the receiving protocol requires an address for each individual data transaction sent. And lastly, we need a control unit. But what is the control unit? The control unit is the merged finite state machine we have been building throughout this flow. Its Verilog implementation simply looks like a large case statement containing the state transitions and a lookup table containing the control signals needed to negotiate transactions between the two IPs, our translator forms the bridge between. The index to this lookup table is simply the state managed by the case statement. We have made it through the full flow. Now, to show some results we have acquired running our tool on some example protocols. To generate results, we wrote PDL code modeling the following protocols: AHB, AXI, our custom packet-based protocol, and tile link. For the 4 protocols, we have 12 translator permutations we run through the flow. In the table shown here, we display these results, including the runtime, cell count, and area of the designs after both synthesis and place and route in 28 nanometer technology. We also show some layouts for a pair of translators. One significant takeaway from this table is the exceptionally low runtime enabled by our FSM integration algorithm, which is, in the maximum case, 1.56 seconds. One advantage of automating translator generation is the ability to customize what functionality of the protocol your IP uses. This is especially useful when you consider that most features in a large, complex protocol are rarely used. So as an experiment, we remove rarely used features in the PDL code for all the translators and rerun the flow. So some examples of what we removed are like non-binary burst transactions, the wrapping burst mode available in AHB and AXI, write protection bits. We removed others that were similar in nature and that I myself have not used before. And our results are good. Our results demonstrate roughly 29 to 34% area reduction for simply deleting code. So hence, if your IP doesn't use particular transactions, you can save on area costs by tightening the specification of your protocol. So in summary, rapid integration of various IP requires either translators or protocol standardization. To solve this problem, we present a new language and algorithms to automatically generate translators. We implement these ideas in C++ code and demonstrate 2 main advantages. First, we show a 29 to 34% area reduction by trimming the specification of the PDL. And second, we greatly reduce engineering effort required to produce these translators. This is especially true when you consider that once our library contains a PDL, it does not need to be written again, and hence the number of translators we can generate grows as a function of n squared. So a user should only need to specify their own custom protocol and then be able to generate translators to other protocols in seconds.